Hello, and welcome to this episode on deep learning and the application in laryngology. We have searched the medical literature for deep learning and the vocal folds from the library of the Royal Society of Medicine, UK. Our focus was on the application of deep learning techniques on imaging. We have not included other voice parameters. Many of the papers that we present today are proof of concept, meaning that further development is often needed for real-world application. As a side note, not all of the papers mention using Python, but we assume they all do, due to it being the prominent language for machine learning and neural networks. Some of the papers use experienced evaluators as ground truth for testing the accuracy of their respective neural networks, while others compare man to machine in order to evaluate if the neural networks outperform inexperienced examiners. We have divided the papers found by our search at Royal Society of Medicine Library into categories. The first one being tracking of vocal folds. These papers focus on moving vocal folds for their function. Other studies focus on classification of single images. Some of the studies describe how they chose a single image. It is worth noting that only one of the three papers utilized high-speed video for optimal visualization of the vocal fold movement. The two others are focused on binary classification between normal and a single diagnosis, which is why the results are measured in sensitivity and specificity, and the high-speed performance is measured in dice coefficient. This article by Wang and co-authors from 2020 on automated glottic tracking for vocal fold paralysis evaluates the application of the tracking software Agati, automated glottic action tracking by artificial intelligence, for quantitative assessment of unilateral vocal fold paralysis with a 77% sensitivity and a 92% specificity between control and paralysis patients. This article from Adamian and co-authors from 2021 is based upon the same software as the previous article, but focuses on predicting unilateral vocal fold paralysis, maximum opening angle less than 58.65 degree, predicted unilateral vocal fold paralysis with a sensitivity of 85% and a specificity of 85%. The focus of this article by Feeling and co-authors from 2020 is on the segmentation of vocal folds in high-speed videos for quantitative analysis. The quantitative analysis of high-speed videos is dependent on the segmentation to be as precise as possible for the best result. Manual segmentation is often slow or inaccurate. This article seeks to determine which neural network is the most precise at automatic segmentation of the vocal folds. 18 different convolutional neural networks were trained on 13,000 high-speed video frames and compared to the ground truth for precision measured with dice coefficient. The highest performing network was a convolutional neural network using long short-term memory. Overall test data resulted in a mean dice coefficient of 85% for glottis, 91% for the right vocal fold, and 90% for the left vocal fold. The papers in this category are based on chromography and phonovibrograms for the datasets. Although these are based on high-speed video, they are transformed from multiple images to a single image of the vocal fold edges movement in time. This changes the possibilities for diagnosis. This trades faster speeds for loss of information. The chromograms are based on a chosen line intersecting the vocal folds. This paper by Yusuf and co-authors from 2021 researched the possibility for using a hybrid approach to detecting the vocal fold edges during vibration, utilizing 116,543 frames from a single subject reading a text using unsupervised machine learning and combining with active contour modeling to capture the edges of vocal folds on chromograms from high-speed video. The results showed an accuracy of 97.4% with an error of plus minus 1 pixel. This is an article from 2003 by Eichhold and co-authors. The reason for including it is that it paved the way for analyzing high-speed videos regarding functionality, using computer simulation on chromograms from high-speed videos with 2000 frames per second. This paper by Unger and co-authors from 2014 aims to discriminate between T1A carcinoma and hyperkeratosis using a support vector machine learning algorithm. It analyzes 15,000 frames of 30 subjects from phonovibrograms based on high-speed video. Phonovibrography is not a cross-section of the vocal folds as chromography, but it visualizes the opening and closing of the vocal folds in time in a similar fashion. The edges are not as precise on phonovibrograms. The purpose is to discern objects obstructing the lumen from glottis, making it possible to detect abnormalities. The quantitative measurements are discussed. The result is a classification between precancerous lesions and T1A carcinoma with a specificity of 100% and a sensitivity of 100%, although the authors suggest a large-scale study to verify their findings. The papers in this category examine the possibility for classifying common diagnosis of the vocal folds. There is focused on randomized single images of the larynx. The selection process is not well described. This paper by Asam and co-authors from 2021 aims to detect laryngeal squamous cell carcinoma from video laryngoscopy. They use a "you only look once" deep learning convolutional neural network for optimal detection accuracy, coupled with acceptable computational complexity. A total of 624 single video frames from 219 subjects were used to train, test, and validate the models. The result was 66% precision and 62% sensitivity. This paper by Parker and co-authors from 2020 focuses on the possibility for classification of granulomas and ulcerations by laryngoscopy. They use a convolutional neural network for image detection and trained it on 100 images and tested it on 27. This resulted in a sensitivity of 82% for granulomas and 62.8% for ulcerations, and a specificity of 99% for granulomas and 99.6% for ulcerations. This is per pixel. This paper by Cho and co-authors from 2021 tests whether a deep neural network can be used to classify various laryngeal diseases better than trainees. A total of 4,106 single images were analyzed. They compared the results between different neural networks and concludes that EfficientNet-B0 had a higher validation accuracy. The neural network outperformed the visual assessment of the trainees in discriminating cysts, granulomas, nodules, normal cases, palsies, papillomas, and polyps. This paper by Ren and co-authors from 2020 tests a convolutional neural network with 24,667 laryngoscopic images for training and testing. 12 otolaryngologists' visual assessment of vocal nodules, polyps, leukoplakia, malignancy, and normal cases were compared to the neural network. The neural network was pre-trained on a dataset from ImageNet with 1.2 million images, using the interesting transfer learning for increased performance. Transfer learning is a technique to train a neural network and gain knowledge on one dataset and apply the knowledge to a different dataset. This resulted in an overall accuracy of 96.24%, with sensitivities ranging from 89% to 99%, and specificity ranging from 98.9% to 99.7%. Comparing neural networks is an important aspect for clinical use. None of the neural networks are till now in routine use. This is in opposition to what is the case in ophthalmology and dermatology. Matava and co-authors sought to develop a machine learning algorithm for classifying vocal cords and tracheal rings real-time during video laryngoscopy for airway management and bronchoscopy. They compared the accuracy of three neural networks: ResNet, Inception, MobileNet version 1, on a dataset of 775 videos. The two best performing neural networks were additionally trained using transfer learning to further test if this would increase the accuracy. The accuracy was 84% for ResNet, 78% for Inception, and 64% for MobileNet version 1. The sensitivity of ResNet improved from 85.1% to 89.2%, and Inception improved from 75.7% to 86.5% with transfer learning. This paper by Zhou and co-authors from 2020 compares four convolutional neural networks trained and tested on 2,216 single images of normal and abnormal vocal folds. A six-layer constructed convolutional neural network was compared to VGG16, Inception version 3, and Exception. This resulted in an accuracy on the six-layer convolutional neural network of 82.2%, VGG16 of 99.7%, Inception version 3 of 99.1%, and Exception of 83.8%. The two best performing networks, VGG16 and Inception version 3, had a sensitivity of 100% and 99.3% respectively. Supporting studies of interest include neural networks for gastroesophageal reflux and optimizing pictures of high-speed videos for quantification. This paper by Wang and co-authors from 2021 proposes a deep learning model for automatic severity grading of gastroesophageal reflux disease called GERD-VGG-Net. They compared four neural networks: VGG16, ResNet 50, ResNet 101, and Inception version 3, trained on 464 subjects and tested on 32 subjects. VGG16 consumed the least amount of CPU time and tied with ResNet 101 on accuracy, and was therefore chosen as basis for the proposed neural network GERD-VGG-Net. This resulted in an accuracy of 87.9% on the test set, which was significantly higher than the results of the two trainees, with an accuracy of 75% and 65.6%. This paper, by Gomez and co-authors from 2019, focuses on the image quality of laryngoscopic images from high-speed video due to low lighting. The approach to enhance low-light images using a convolutional neural network is compared against four state-of-the-art low-light enhancement methods and statistically outperforms each on a no reference and two full reference image quality metrics. The proposed convolutional neural network was closest to the 3.6 of the original image on the Nick metric score with 5.0 compared to the four low-light enhancement methods ranging from 10.03 to 10.93. Thank you for watching.